Hi everyone. I'm Vanjikumaran from California. It's right now over here. It's midnight, 1:45 a.m. At the same time, I'm working as a solution engineer with WSO2. It's an open source integration company. During my free time, I volunteer with the Apache Synapse project as a project committee member and the committer. In this talk, I will be mainly cover more about Microsoft microservices architecture and how to optimize the mean time to detect, or it's well known as a MTTD. Let's go ahead without spending any further time. So as a very first step, we have to quickly review what is the monolithic architecture means, so that I have created a very simple monolithic application architecture to give an overview. So for example, I have created the illustration over here to depict point of sales application functionality to show a very simple monolithic application behavior. So over here, the functionalities are packaged together as one single package and exposed and interconnected to external systems. Regardless of the logical modulars, the application is packaged as one single monolithic application. And the packagings completely depend on the languages. For example, it could be War or Java if it is Java, and even the directory structure also completely depend on the languages that we choose. But it may be simple to test and deploy, and if it is simple, and what's the issue, right? Why we are too worried about monolithic application? Simple and easy only at the beginning. As the application grow and when we add more functionalities, more and more, there will be lots of drawbacks and pain points. And one of that is the increasingly difficult to maintain the code changes. And it disrupts the agile development. Over the time, no single developer will understand the entire code. Changes will be error prone. At the same time, continuous integration, continuous delivery would be very painful because of the nature of single monolithic applications behavior. At the same time, the scaling would be so difficult. The reason is now, for example, in the previous image that I show you, within that POS application, there is an order functionality. And when there is a demand for increasing the order functionality, you may have to scale up entire POS application itself rather than only that order module. So if there is an issue in one single component, the potentially it can bring down the entire application. At the same time, mostly you may have to stick with one single language, which means then you have to find the talent and the people who know that language only, rather than like you can to bring polynomic way of implementing the application by bringing more different knowledge people. So single code size grow over the time, and it would become very hard and increasingly difficult for a single developer to understand entire code, as I already mentioned. Hence, it would be difficult for any changes that we can make on and make the CI/CD process, say, weekly. At the same time, it also consume the lots of hardware resources, like CPU incentive component could make like entire hardware compared to memory intensive components. So you have to make lots of compromise just in order to adapt this. So what would be a solution? There are lots of solutions, but one of them is microservices. So the same POS application, what I have done over here, I have illustrated and transformed the previously discussed monolithic POS application into microservices architecture. So as you can see, now each and every functionality break into different deployable independent modules. and the communication between these modules and functionalities are governed by a standard protocol. For example, over here I have chosen RESTful API. So to summarize what we discussed previously with regard to the microservices architecture, an application written in as a small interconnected services, and each are independent, distinct functionalities. So which mean it's self-contained and maintain its own data stores and databases. Each services may expose a REST service or any other standard protocols, for example, gRPC or something like that. So those services can be accessed through the network. So the service may also use other inter-protocol communication methods such as queues or JMS and so on and so forth. Further, the microservices could implement a simple web UI and not expose REST API, and that is possible in the microservices world. At the same time, a microservice does not necessarily expose API, but usually it does. At the same time, microservices could communicate via other means of communication protocols that I already mentioned that we have to understand. So this means the separate database and different set of protocols ensure the loose coupling between the components. At the same time, it also guarantees the duplicate data being avoided. So a few advantage thinking of a microservices architecture over here. We can do very fast and focused development, easy to do the deployment through the continuous integration, continuous delivery process. So due to the less dependency nature of microservices architecture. At the same time, as we already discussed, we can scale based on the demand, and it's much more flexible for us. We don't need to scale the complete application, but only the particular module that we are interested in. At the same time, we also can reduce the downtime due to the modularity. In the case of, for example, if there is a bug or issue, or you want to do a maintenance for particular functionality, you don't need to bring down entire application. You just can update one single functionality because of the modular nature of it. Further, the application also become a much more cloud native rather than just a cloud friendly. And which allow you to explore all the possible tools and infrastructure that we have in front of us currently. But I mean, it's like same like any other architecture. There's also lots of drawbacks and pain points with the microservices architecture. So one of the main point over here, pain point over here is we really don't know what we really mean by microservices. What is the size limit of the microservices, or whether it's 300 lines of code or 10,000 lines of code. We still don't have a proper answer for that, but it only governed by how the functionalities are broken into the pieces. But considering the modularity and the interconnection communication, there is an inherent complexity of distribution of system handling and transaction. So which means there are lots of chances to get all the real network problems. So in today's talk, I will mainly focus on this particular point. How we can avoid these, and how we can observe and create proper procedures to avoid this. Going forward, another drawback of this, there is lots of duplicatable multiple different databases involved. So if you really want to maintain the consistency across the database, there need to be update with multiple database for consistency. At the same time, in a cloud native container based microservices, the hard-coded endpoints are not an option. You do not know the endpoints during the design time. It will only reveal during the runtime. So the service discoveries, at the same time, the need for the advanced technologies like service mesh, service discovery, circuit breakers, containers, orchestrations are required. So as I mentioned, we know that there is a complexity and there is an issue with the network and everything. So in industry, there are two concepts well known. One is mean time to recovery, was a mean time to detect. So idea of these concepts are widely used in tech industry, regardless of whether it's a monolithic or microservices architecture. So as a very first thing, we should understand the significance of the difference between MTTR and MTTD. So as a very first step, let's think about what does it mean by mean time to recover. So mean time to recover deals with after the incident or issue happen, how quickly you can recover back from the incident, which means the damage is already done, how you can avoid the further damage and how you can get back to the normal state. So as you see in the picture, the damage is already done. So now we had to quickly fix the issue and give the production or client the fix very fast to recover back to the normal stage. But whereas the MTTD is pretty much deal with how quickly you can identify the issue and minimize the occurrence of the issue by utilizing all the tools and protocols and best practices in place, so that you don't need to get into the mean time to recovery part. You can just find out the issue before it happens. So there are multiple ways of doing it. So one way is as very simple amateur mechanic. You can try to do one by one or put the simple things like looking into the logs and examining through the code, or after the putting up errors, error catch. Likewise, you can do some amateur type of work, but at the same time, if a pro mechanic who's discovering the issues or diagnosing the issues, there are enough tools in the market. And what we are going to look into next 10 to 15 minutes, what are the techniques and the tools that we have in the industry. So with the organizations are moving from monolithic architecture to distributed microservices architecture along with cloud native adoption, these environments include thousands of components interacting in complex, rapidly changed deployments over the multiple tiers. So therefore, there will be large number of events, metrics, and data are produced in each and every layers and nodes. So today's dynamic cloud native environment use multiple different technologies to aggregate this tool. Currently in industry, there are two techniques utilized for monitoring. One is known as observability and other one is surveillance. So what we are going to do in upcoming discussion, we will be getting into the detail, and I will introduce few tools so that you can employ those. So if there is no proper system of monitoring or observing the ecosystem, organization will never be able to quickly detect or resolve the damaging problem. Hence, going forward, we will understand this tooling. Right. So observability is one of the critical pillar of reducing the mean time to detect. By definition, observability is collecting the diagnostic data across all the stacks to identify and debug production problem, and also provide critical signals about usage to enable a highly adaptive and scalable system. Observability is primarily driven by 6 different dimensions to understand the environment. So one of that is monitoring. Second is log aggregation. The third one is tracing. Fourth is visualization, alerting, and people. So we will look in one by one. Monitoring. A fundamental aspect of monitoring is to collect, process, aggregate, and display real-time quantitative data about the ecosystem and measure metrics in 3 different layers in our case. One is network, and then mission level and application level. So such a monitoring will produce different error counts and different processing time, memory usage, server lifetime. For example, over here, I have taken a very simple screenshot of a particular mission or the JVM about the memory utilization and the CPU utilization, so that we can see whether the application, whether is it overutilizing the processing power, whether it's overutilizing the memory, and if it is overutilizing, will it go to the out of memory situation, such like that. So the second, I mean, at the same time, another example that I can think of is monitoring performance of a given JVM based on application. That's very simply, you can monitor using the JConsole or collecting the metrics of CPU utilization or memory utilization or number of threads, etc. But this is pretty amateurish approach because if you really want to monitor each and every application one by one, it's a complete nightmare for any DevOps or the network team or the owners of the application. So to do that, I mean, in the industry, there is a concept known as application performance monitoring, or well known as APM. So most of the large enterprise distributed application owners, it's not, I mean, as I mentioned, not feasible just to target monitor a single JVM machine. So instead of what they're doing is they will utilize the application performance monitor tools, and it's in place to facilitate monitor multiple functional dimensions. For example, the tools like Dynatrace, AppDynamics, Neuralink, Datadog, and even open source tool like Apache Skyworking, completely fully fledged monitoring tools which provide complete analytic capable for the APM needs. So in this picture, I mean, there are multiple machines and JVMs connected with the databases, and how the interaction, what is the memory utilization, then how the network traffic and everything are understood in one single big picture. So the next one is tracing. So traditionally, monolithic application employed a logging framework to provide insight on what's happening if something failed in the system. To understand or recognize the failure, looking at the log statements and correlating the timestamp and the context is more than enough, and the most of the information will reveal through that logs if it is correctly defined in the development time. However, in the distributed microservices architecture, having a log is not enough at all to understand the bigger picture. So tracing can be easily understood by analogy of medical angiogram. So the angiogram is a technique to find the blocks in heart by injecting an X-ray sensitive dye, which make a block detection. The example that I have put in the picture over here. So the possible, the dynamic X-ray snapshot will reveal the moving dyes through the blood vessels and detect the bottlenecks in this manner. So the same concept can be utilized in the tracing in our tech world, especially the software implementation. So likewise, tracing is heavily utilized in a distributed software ecosystem to profile and monitor the communication or transaction between multiple systems, including networks and applications. So further tracing also help to understand the flows between different services and give a bigger overview of application level of transparency. So there are tools, open source tools and commercial tools like Zipkin, Jaeger, Instana, Datadog, Apache Skyworking, and AppDash tools in the market. Those are the very few examples that I can tell you about enabling the distributed tracing tools to support open tracing and open telemetric specification. So the tracing is now much more standardized. Right now, the very popular standard is open tracing, but upcoming standard is open telemetry as a specification. So the next level of tools, what we are going to discuss over here is the log aggregation. So there are endless different varieties of logs, like application logs, security logs, audit logs, access log, and more. In a single application, you can find all of these complex different type of log, and it's really hard to manage all of these together in one single place. And at the same time, in the distributed architecture, there may be different applications and service working together to complete a single business functionality. For example, if I'm ordering a pizza, means I have to have a different application to store availability, making the payment, placing the order, fulfill the order, enable the tracking, shipping schedule, placement, and many other activities. In one single event, if there is one single error in such a complex transaction, the tracing and the pinpointing the exact location of the root cause is nightmare. So, however, if the application-centric logs are distributed across different components, what we can do is we can have a centralized location to aggregate all of these logs by different indexes, and we can at the same time correlate these logs together to detect the exact location of the issue much more efficiently. So currently there are many tools and softwares in the market to achieve the log aggregations. One example is Splunk, other one is Sumo Logic, Elastic, Gray Log. They play a really important role in the log aggregation market. So the next level of is the visualization. So there are tools that can collect the data, logs, and metrics in central location. But however, collecting the data and log does not provide any meaningful information. So in order to make them useful, what we can do is we can make use of the data visualization to depict the holistic view based on the criteria provided. For example, in this case, I really want to locate the host, which most number of error messages that can be identified easily in the visualization in this case. Over here, easily I can look into the error count, which is more than 1,500, and locate the host name and access it. Another epic example is to correlate two different errors happen in the separate host and or the application, and see the time series aggregation charts, for example, over here. So in this case, what I'm doing is I'm correlating two applications. I mean, to see how these two services and applications are matching during the production issue time, or when there is a spike in the usage of the application. So the visualization of the data not only restrict restricted to errors or exception, but also it can be utilized to understand the behavioral monitoring of the application users. For example, if there is an overuse API user, we can identify and put it into the data visualization and detect the abusive behavior right away. So we do have most of the information right now, but with having alerting is very crucial component. The reason for that, searching through the logs and data can be helpful to speed up the debugging process and resolve the issue. But in reality, the manual monitoring and visualization to detect the incidents are not practical. So creating automated alerts are critical. Common scenarios that well known required alerts include sudden failure of one or more API, sudden increase in the response time, or one or more API is crucial. Then looking in the pattern of the API access and the resource access is also very important. In this case, what I have done is created an alert which alert me if when there is the surge of utilization at the same time if the response time is too high. So these alerts can be email, phone calls, instant message, or PagerDuty, any type of thing. But it's very important aspect that we should be able to define these alerts so that we can really look into the bigger picture about how the predefined condition is met or violated, if the necessary stakeholders been notified or not, likewise. So this brings us to a conclusion where the surveillance, the collecting the data in random manner with the different views of the same random data does not going to reveal anything at all. For example, the real world surveillance, like a real world surveillance used to monitor the activities by police or securities, it also can be utilized for later evidence as a crime or facts. For example, over here, if you're looking into the picture, we are putting many surveillance camera, but everywhere. I mean, having untargeted surveillance never going to help us. So we should be able to have the surveillance used to force the targeted observation of the system to make sure the functionalities and performance are not violating the intended behavior. So the real world surveillance can be compared with the other software world as well. So for example, over here, I have put a very simple surveillance for my memory utilization. When there is a high memory utilization or when there is a possible out of memory situation, it will give me the alert, and so that we can act very fast to detect the memory leaks or abnormal memory utilization and avoid the uninterrupted services. So as a conclusion, optimizing the infrastructure for minimizing the mean time to detect the incidents with the microservices architecture that ensure that organization has established appropriate systematic techniques to employ observability and surveillance technologies effectively to find out the incident right way to keep the system stable. So with that, thanks a lot. If there is any question, I'm happy to answer.